1/8 below the holes in the main discharge nozzle. The fuel level must be maintained slightly below the discharge nozzle outlet holes to provide the correct amount of fuel flow and to prevent fuel leakage from the nozzle when the engine is not operating. The level of fuel in the float chamber is kept nearly constant by means of a float-operated needle valve and a seat. The needle seat is usually made of bronze. The needle valve is constructed of hardened steel, or it may have a synthetic rubber section which fits the seat. With no fuel in the float chamber, the float drops toward the bottom of the chamber and allows the needle valve to open wide. As fuel is admitted from the supply line, the float rises, floats in the fuel, and closes the needle valve when the fuel reaches a predetermined level. When the engine is running, and fuel is being drawn out of the float chamber, the valve assumes an intermediate position, so that the valve opening is just sufficient to supply the required amount of fuel and keep the level constant. Figure 2-10. With the fuel at the correct level, float chamber, the discharge rate is controlled accurately by the air velocity through the carburetor venturi, where a pressure drop at the discharge nozzle causes fuel to flow into the intake airstream. Atmospheric pressure on top of the fuel in the float chamber forces the fuel out the discharge nozzle. A vent or small opening in the top of the float chamber allows air to enter or leave the chamber as the level of fuel rises or falls. Main metering system. The main metering system supplies fuel to the engine at all speeds above idling and consists of 1. Venturi 2. Main metering jet 3. Main discharge nozzle 4. Passage leading to the idling system 5. Throttle valve. Since the throttle valve controls the mass airflow through the carburetor venturi, it must be considered a major unit in the main metering system as well as in other carburetor systems. A typical main metering system is illustrated in Figure 2-12. The venturi performs 3 functions. 1. Proportions the fuel/air mixture. 2. Decreases the pressure at the discharge nozzle. 3. Limits the airflow at full throttle. The fuel discharge nozzle is located in the carburetor barrel, so that its open end is in the throat or narrowest part of the venturi. A main metering orifice, or jet, is placed in the fuel throttle valve. Fuel discharge nozzle. 14.7 Ps. I. Venturi. Main air bleed. Idle feed passage. Airflow. Main metering jet. Figure 2-12. Main metering system. Passage between the float chamber and the discharge nozzle to limit the fuel flow when the throttle valve is wide open. When the engine crankshaft is revolved with the carburetor throttle open, the low pressure created in the intake manifold acts on the air passing through the carburetor barrel. Due to the difference in pressure between the atmosphere and the intake manifold, air flows from the air intake through the carburetor barrel into the intake manifold. The volume of airflow depends upon the degree of throttle opening. As the air flows through the venturi, its velocity increases. This velocity increase creates a low pressure area in the venturi throat. The fuel discharge nozzle is exposed to this low pressure. Since the float chamber is vented to atmospheric pressure, a pressure drop across the discharge nozzle is created. It is this pressure difference, or metering force, that causes fuel to flow from the discharge nozzle. The fuel comes out of the nozzle in a fine spray, and the tiny particles of fuel in the spray quickly vaporize in the air. The metering force pressure differential in most carburetors increases as the throttle opening is increased. The fuel must be raised in the discharge nozzle to a level at which it discharges into the airstream. To accomplish this, a pressure differential of 0.5 Hg is required. When the metering force is considerably reduced at low engine speeds, the fuel 2-11 delivery from the discharge nozzle decreases if an air metering jet is not incorporated in the carburetor. The decrease in fuel flow in relation to airflow is due to 2 factors. 1. The fuel tends to adhere to the walls of the discharge nozzle and break off intermittently in large drops instead of forming a fine spray. And 2. A part of the metering force is required to raise the fuel level from the float chamber level to the discharge nozzle outlet. The basic principle of the air bleed can be explained by simple diagrams, as shown in Figure 2-13. In each case, the same degree of suction is applied to a vertical tube placed in the container of liquid. As shown in the suction applied on the upper end of the tube is sufficient to lift the liquid a distance of about 1 inch above the surface. If a small hole is made in the side of the tube above the surface of the liquid, as in B, and suction is applied, bubbles of air enter the tube and the liquid is drawn up in a continuous series of small slugs or drops. Thus, air bleeds into the tube and partially reduces the forces tending to retard the flow of liquid through the tube. However, the large opening at the bottom of the tube effectively prevents any great amount of suction from being exerted on the air bleed hole or vent. Similarly, an air bleed hole that is too large in proportion to the size of the tube would reduce the suction available to lift the liquid. If the system is modified by placing a metering orifice in the bottom of the tube and air is taken in below the fuel level by means of an air bleed tube, a finely divided mixture of air and liquid is formed in the tube, as shown in C. In a carburetor, a small air bleed is bled into the fuel nozzle slightly below the fuel level. The open end of the air bleed is in the space behind the venturi wall, where the air is relatively motionless, and at approximately atmospheric pressure. The low pressure at the tip of the nozzle not only draws fuel from the float chamber, but also draws air from behind the venturi. Air bled into the main metering fuel system decreases the fuel density and destroys surface tension. This results in better vaporization and control of fuel discharge, especially at lower engine speeds. The throttle, or butterfly valve, is located in the carburetor barrel near one end of the venturi. It provides a means of controlling engine speed or power output by regulating the airflow to the engine. This valve is a disc that can rotate on an axis, so that it can be turned to open or close the carburetor air passage. Idling system. With the throttle valve closed at idling speeds, air velocity through the venturi is so low that it cannot draw enough fuel from the main discharge nozzle. In fact, the spray of fuel may stop altogether. However, low pressure piston suction exists on the engine side of the throttle valve. In order to allow the engine to idle, a fuel passageway is incorporated to discharge fuel from an opening in the low pressure area near the edge of the throttle valve. Figure 2-14. This opening is called the idling jet. With the throttle open enough so that the main discharge nozzle is operating, fuel does not flow out of the idling jet. As soon as the throttle is closed far enough to stop the spray from the main discharge nozzle, fuel flows out the idling jet. A separate air bleed, known as the idle air bleed, is included as part of the idling system. It functions in the same manner as the main air bleed. An idle mixture adjusting device is also incorporated. A typical idling system is illustrated in Figure 2-15. Mixture control system. As altitude increases, the air becomes less dense. At an altitude of 18,000 feet, the air is only half as dense as it is at sea level. This means that a cubic foot of space contains only half as much air at 18,000 feet as at sea level. An engine. Suction. Pinhole. Air. 1 inch. 3/4 inch. Restriction. A. Figure 2-13. Air bleed principle. 2-12. B. C. Figure 2-14. Throttle action in idle position. Idling jet. 11 Ps. I. Idle mixture adjustment. 13.5 Ps. I. 14 Ps. I. Idle air bleed. Figure 2-15. Idling system. Cylinder full of air at 18,000 feet contains only half as much oxygen as a cylinder full of air at sea level. The low pressure area created by the venturi is dependent upon air velocity rather than air density. The action of the venturi draws the same volume of fuel through the discharge nozzle at a high altitude as it does at a low altitude. Therefore, the fuel mixture becomes richer as altitude increases. This can be overcome either by a manual or an automatic mixture control. On float-type carburetors, two types of purely manual or cockpit controllable devices are generally used for controlling fuel/air mixtures, the needle type and the back suction type. Figures 2-16 and 2-17. With the needle type system, manual control is provided by a needle valve in the base of the float chamber. Figure 2-16. This can be raised or lowered by adjusting a control in the cockpit. Moving the control to rich opens the needle valve wide, which permits the fuel to flow unrestricted. M. Full rich. Figure 2-16. Needle type mixture control system. Idle cutoff line. Idle cutoff. Back suction line. Full rich position. Figure 2-17. Back suction type mixture control system. 2-13. To the nozzle. Moving the control to lean partially closes the valve and restricts the flow of fuel to the nozzle. The back suction type mixture control system is the most widely used. Figure 2-17. In this system, a certain amount of venturi low pressure acts upon the fuel in the float chamber so that it opposes the low pressure existing at the main discharge nozzle. An atmospheric line, incorporating an adjustable valve, opens into the float chamber. When the valve is completely closed, pressures on the fuel in the float chamber and at the discharge nozzle are almost equal, and fuel flow is reduced to maximum lean. With the valve wide open, pressure on the fuel in the float chamber is greatest, and fuel mixture is richest. Adjusting the valve to positions between these two extremes controls the mixture. The quadrant in the cockpit is usually marked lean near the back end and rich at the forward end. The extreme back position is marked idle cutoff and is used when stopping the engine. On float carburetors equipped with needle-type mixture control, placing the mixture control in idle cutoff seats the needle valve, thus shutting off fuel flow completely. On carburetors equipped with back suction mixture controls, a separate idle cutoff line, leading to the extreme low pressure on the engine side of the throttle valve, is incorporated. See the dotted line in Figure 2-17. The mixture control is so linked that when it is placed in the idle cutoff position, it opens another passage that leads to piston suction. When placed in other positions, the valve opens a passage leading to the atmosphere. To stop the engine with such a system, close the throttle and place the mixture in the idle cutoff position. Leave the throttle until the engine has stopped running, and then open the throttle completely. Accelerating system. When the throttle valve is opened quickly, a large volume of air rushes through the air passage of the carburetor. The amount of fuel that is mixed with the air is less than normal due to the slow response rate of the main metering system. As a result, after a quick opening of the throttle, the fuel/air mixture lians out momentarily. This can cause the engine to accelerate slowly or stumble as it tries to accelerate. To overcome this tendency, the carburetor is equipped with a small fuel pump called an accelerating pump. A common type of accelerating system used in float carburetors is illustrated in Figure 2-18. It consists of a simple piston pump operated through linkage by the throttle control, and a passageway opening into the main metering system or the carburetor barrel near the venturi. When the throttle is closed, the piston moves back and fuel fills the cylinder. If the piston is pushed forward slowly, the fuel seeps past it back into the float chamber. If pushed rapidly, it sprays fuel in the venturi and force downward. Economizer opening. Figure 2-18. Accelerating system. Enriches the mixture. An example of a cutaway accelerator pump is shown in Figure 2-19. Figure 2-19. Accelerating pump shown in cutaway. Economizer system. For an engine to develop maximum power at full throttle, the fuel mixture must be richer than for cruise. The additional fuel is used for cooling the engine combustion chambers to prevent detonation. An economizer is essentially a valve that is closed at throttle settings below approximately 60-70% of rated power. This system, like the accelerating system, is operated by the throttle control. A typical economizer system consists of a needle valve which begins to open when the throttle valve reaches a predetermined point near the wide open position. Figure 2-20. As the throttle continues to open, the needle. 2-14. Main air bleed. Economizer needle. Main metering jet. Economizer metering jet. Main discharge nozzle. Figure 2-20. A needle valve type economizer system. Valve is opened further and additional fuel flows through it. This additional fuel supplements the flow from the main metering jet direct to the main discharge nozzle. A pressure-operated economizer system is shown in Figure 2-21. This type has a sealed bellows located in an enclosed compartment. The compartment is vented to engine manifold pressure. When the manifold pressure reaches a certain value, the bellows is compressed and opens a valve in a carburetor fuel passage, supplementing the normal quantity of fuel being discharged through the main nozzle. Compression spring, force upward, to manifold pressure. Fulcrum. Dashpot. Evacuated bellows, force downward, economizer opening automatically controlled by supercharger pressure. Figure 2-21. A pressure-operated economizer system. Another type of economizer is the back suction system. Figure 2-22. Fuel economy in cruising is provided by reducing the effective pressure acting on the fuel level in the float compartment. With the throttle valve in cruising position, suction is applied to the float chamber through an economizer hole, and back suction economizer channel and jet. The suction applied to the float chamber opposes the nozzle suction applied by the venturi. Fuel flow is reduced, leaning the mixture for cruising economy. Main air bleed. Back suction economizer channel and jet. Vent. Main discharge nozzle. Air. Main metering jet. Figure 2-22. Pressure type carburetor. Another type of mixture control system uses a metering valve that is free to rotate in a stationary metering sleeve. Fuel enters the main and idling systems through a slot cut in the mixture sleeve. Fuel metering is accomplished by the relative position between one edge of the slot in the hollow metering valve and one edge of the slot in the metering sleeve. Moving the mixture control to reduce the size of the slot provides a leaner mixture for altitude compensation. Pressure injection carburetors. Pressure injection carburetors are distinctly different from float-type carburetors as they do not incorporate a vented float chamber or suction pickup from a discharge nozzle located in the venturi tube. Instead, they provide a pressurized fuel system that is closed from the engine fuel pump to the discharge nozzle. The venturi serves only to create pressure differentials for controlling the quantity of fuel to the metering jet in proportion to airflow to the engine. Typical injection carburetor. The injection carburetor is a hydromechanical device employing a closed feed system from the fuel pump to the 2-15 discharge nozzle. It meters fuel through fixed jets according to the mass airflow through the throttle body and discharges it under a positive pressure. The illustration in Figure 2-23 represents a pressure-type carburetor simplified so that only the basic parts are shown. Note the two small passages, one leading from the carburetor air inlet to the left side of the flexible diaphragm, and the other from the venturi throat to the right side of the diaphragm. Diaphragm. Fuel valve. Discharge nozzle fuel intake line. Figure 2-23. Pressure-type carburetor. When air passes through the carburetor to the engine, the pressure on the right of the diaphragm is lower because of the drop in pressure at the venturi throat. As a result, the diaphragm moves to the right, opening the fuel valve. Pressure from the engine-driven pump then forces fuel through the open valve to the discharge nozzle, where it sprays into the airstream. The distance the fuel valve opens is determined by the difference between the two pressures acting on the diaphragm. This difference in pressure is proportional to the airflow through the carburetor. Thus, the volume of airflow determines the rate of fuel discharge. The pressure injection carburetor is an assembly of the following units. 1. Throttle body. 2. Automatic mixture control. 3. Regulator unit. 4. Fuel control unit. Some are equipped with an adapter. Throttle body. The throttle body contains the throttle valves, main venturi, boost venturi, and the impact tubes. All air entering the cylinders must flow through the throttle body. Therefore, it is the air control and measuring device. The airflow is measured by volume and by weight so that the proper amount of fuel can be added to meet the engine demands under all conditions. As air flows through the venturi, its velocity is increased and its pressure is decreased. Bernoulli's principle. This low pressure is vented to the low pressure side of the air diaphragm, figure 2-24 chamber B in the regulator assembly. The impact tube sends carburetor inlet air pressure and direct it to the automatic mixture control, which measures the air density. From the automatic mixture control, the air is directed to the high pressure side of the air diaphragm, chamber A. The pressure differential of the two chambers acting upon the air diaphragm is known as the air metering force, which opens the fuel pipette valve. Vent chamber, idle spring, vapor separator, ABCDE, balance diaphragm, sealing diaphragm, pipette valve and diaphragm, air diaphragm, fuel strainer, mixture control bleeds, fuel inlet, dual diaphragm, fuel pressure gauge connection, figure 2-24. Regulator unit. The throttle body controls the airflow with the throttle valves. The throttle valves may be either rectangular or disc-shaped, depending on the design of the carburetor. The valves are mounted on a shaft, which is connected by linkage to the idle valve, and to the throttle control in the cockpit. A throttle stop limits the travel of the throttle valve, and has an adjustment, which sets engine idle speed. Regulator unit. The regulator is a diaphragm-controlled unit divided into 5 chambers, and contains 2 regulating diaphragms and a pipette valve assembly. Figure 2-24. Chamber A is regulated air inlet pressure from the air intake. Chamber B is boost venturi pressure. Chamber C contains metered fuel. 2-16. Pressure controlled by the discharge nozzle or fuel feed valve. Chamber D contains unmetered fuel pressure controlled by the opening of the pipette valve. Chamber E is fuel pump pressure controlled by the fuel pump pressure relief valve. The pipette valve assembly is connected by a stem to the 2 main control diaphragms. The purpose of the regulator unit is to regulate the fuel pressure to the inlet side of the metering jets in the fuel control unit. This pressure is automatically regulated according to the mass airflow to the engine. The carburetor fuel strainer, located in the inlet to chamber E, is a fine mesh screen through which all the fuel must pass as it enters chamber D. The strainer must be removed and cleaned at scheduled intervals. Referring to figure 2-24. Assume that for a given airflow in pounds/hour through the throttle body and venturi, a negative pressure of 1/4 psi is established in chamber B. This tends to move the diaphragm assembly and the pipette valve in a direction to open the pipette valve, permitting more fuel to enter chamber D. The pressure in chamber C is held constant at 5 psi, 10 psi on some installations, by the discharge nozzle or impeller fuel feed valve. Therefore, the diaphragm assembly and pipette valve moves in the open direction until the pressure in chamber D is 5 1/4 psi. Under these pressures, there is a balanced condition of the diaphragm assembly with a pressure drop of 1/4 psi across the jets in the fuel control unit, auto-rich or auto-lean. If nozzle pressure, chamber C pressure, rises to 5 1/2 psi, the diaphragm assembly balance is upset, and the diaphragm assembly moves to open the pipette valve to establish the necessary 5 3/4 psi pressure in chamber D. Thus, the 1/4 psi differential between chamber C and chamber D is re-established, and the pressure drop across the metering jets remains the same. If the fuel inlet pressure is increased or decreased, the fuel flow into chamber D tends to increase or decrease with the pressure change, causing the chamber D pressure to do likewise. This upsets the balanced condition previously established, and the pipette valve and diaphragm assembly respond by moving to increase or decrease the flow to re-establish the pressure at the 1/4 psi differential. The fuel flow changes when the mixture control plates are moved from auto-lean to auto-rich, thereby selecting a different set of jets or cutting 1 or 2 in or out of the system. When the mixture position is altered, the diaphragm and pipette valve assembly repositions to maintain the established pressure differential of 1/4 psi between chamber C and D, maintaining the established differential across the jets. Under low power settings, low airflows, the difference in pressure created by the boost venturi is not sufficient to accomplish consistent regulation of the fuel. Therefore, an idle spring, shown in figure 2-24, is incorporated in the regulator. As the pipette valve moves toward the closed position, it contacts the idle spring. The spring holds the pipette valve off its seat far enough to provide more fuel than is needed for idling. This potentially over-rich mixture is regulated by the idle valve. At idling speed, the idle valve restricts the fuel flow to the proper amount. At higher speeds, it is withdrawn from the fuel passage and has no metering effect. Vapor vent systems are provided in these carburetors to eliminate fuel vapor created by the fuel pump, heat in the engine compartment, and the pressure drop across the pipette valve. The vapor vent is located in the fuel inlet, chamber E, or, on some models of carburetors, in both chambers D and D. The vapor vent system operates in the following way. When air enters the chamber in which the vapor vent is installed, the air rises to the top of the chamber, displacing the fuel and lowering its level. When the fuel level has reached a predetermined position, the float, which floats in the fuel, pulls the vapor vent valve off its seat, permitting the vapor in the chamber to escape through the vapor vent seat, its connecting line, and back to the fuel tank. If the vapor vent valve sticks in a closed position or the vent line from the vapor vent to the fuel tank becomes clogged, The vapor eliminating action is stopped. This causes the vapor to build up within the carburetor to the extent that vapor passes through the metering jets with the fuel. With a given size carburetor metering jet, the metering of vapor reduces the quantity of fuel metered. This causes the fuel/air mixture to lean out, usually intermittently. If the vapor vent valve sticks open, or the vapor vent float becomes filled with fuel and sinks, a continuous flow of fuel and vapor occurs through the vent line. It is important to detect this condition, as the fuel flow from the carburetor to the fuel supply tank may cause an overflowing tank with resultant increased fuel consumption. To check the vent system, disconnect the vapor vent line where it attaches to the carburetor, and turn the fuel booster pump on while observing the vapor vent connection at the carburetor. Move the carburetor mixture control to auto-rich, then return it to idle cutoff. When the fuel booster pump is turned on, there should be an initial ejection of fuel and air followed by a cutoff with not more than a steady drip from the vent connection. Installations with a fixed bleed from the D chamber connected to the vapor vent in the fuel inlet by a short external line should show an initial ejection of fuel and air followed by a continuing small stream of fuel. If there 2-17 is no flow, the valve is sticking closed. If there is a steady flow, it is sticking open. Fuel control unit. The fuel control unit is attached to the regulator assembly and contains all metering jets and valves. Figure 2-25, the idle and power enrichment valves, together with the mixture control plates. Select the jet combinations for the various settings, that is, auto-rich, auto-lean, and idle cutoff. Manual mixture control. Idle needle valve. Auto-lean jet. Regulator fill valve. Auto-rich jet. Power enrichment valve. Power enrichment jet. Figure 2-25. Fuel control unit. The purpose of the fuel control unit is to meter and control the fuel flow to the discharge nozzle. The basic unit consists of 3 jets and 4 valves arranged in series, parallel, and series parallel hookups. Figure 2-25. These jets and valves receive fuel under pressure from the regulator unit, and then meter the fuel as it flows to the discharge nozzle. The manual mixture control valve controls the fuel flow. By using proper size jets and regulating the pressure differential across the jets, the right amount of fuel is delivered to the discharge nozzle, giving the desired fuel/air ratio in the various power settings. It should be remembered that the inlet pressure to the jets is regulated by the regulator unit and the outlet pressure is controlled by the discharge nozzle. The jets in the basic fuel control unit are the auto-lean jet, the auto-rich jet, and power enrichment jet. The basic fuel flow is the fuel required to run the engine with a lean mixture and is metered by the auto-lean jet. The auto-rich jet adds enough fuel to the basic flow to give a slightly richer mixture than best power mixture when the manual mixture control is in the auto-rich position. The 4 valves in the basic fuel control unit are 1. Idle needle valve. 2. Power enrichment valve. 3. Regulator fill valve. 4. Manual mixture control. The functions of these valves are 1. The idle needle valve meters the fuel in the idle range only. It is a round, contoured needle valve, or a cylinder valve placed in series with all other metering devices of the basic fuel control unit. The idle needle valve is connected by linkage to the throttle shaft, so that it restricts the fuel flowing at low power settings, idle range. 2. The manual mixture control is a rotary disc valve consisting of a round stationary disc with ports leading from the auto-lean jet, the auto-rich jet, and 2 smaller vent holes. Another rotating part, resembling a cloverleaf, is held against the stationary disc by spring tension, and rotated over the ports in that disc by the manual mixture control lever. All ports and vents are closed in the idle cutoff position. In the auto-lean position, the ports from the auto-lean jet and the 2 vent holes are open. The port from the auto-rich jet remains closed in this position. In the auto-rich position, all ports are open. The valve plate positions are illustrated in figure 2-26. The 3 positions of the manual mixture control lever make it possible to select a lean mixture, a rich mixture, or to stop fuel flow entirely. The idle cutoff position is used for starting or stopping the engine. During starting, fuel is supplied by the primer. 3. The regulator fill valve is a small pipette-type valve located in a fuel passage, which supplies chamber C of the regulator unit with metered fuel pressure. In idle cutoff, the flat portion of the cam lines up with the valve stem, and a spring closes the valve. This provides a means of shutting off the fuel flow to chamber C and thus provides for a positive idle cutoff. 4. The power enrichment valve is another pipette-type valve. It is in parallel with the auto-lean and auto-rich jets, but it is in series with the power enrichment jet. This valve starts to open at the beginning of the power range. It is opened by the unmetered fuel pressure overcoming metered fuel pressure and spring tension. The power enrichment valve continues to open wider during the power range until the combined flow through the valve and the auto-rich jet exceeds that of the power enrichment jet. At this point the power 2-18 vent channel from chamber D, channel from auto-rich jet, channel from auto-lean jet, vent for space above valve, full rich auto-lean auto-rich idle cutoff. Figure 2-26. Manual mixture control valve plate positions. Enrichment jet takes over the metering and meters fuel throughout the power range. 5. Carburetors equipped for water injection are modified by the addition of a dirichment valve and a dirichment jet. The dirichment valve and dirichment jet are in series with each other and parallel with the power enrichment jet. The carburetor controls fuel flow by varying two basic factors. The fuel control unit, acting as a pressure-reducing valve, determines the metering pressure in response to the metering forces. The regulator unit, in effect, varies the size of the orifice through which the metering pressure forces the fuel. It is a basic law of hydraulics that the amount of fluid that passes through an orifice varies with the size of the orifice and the pressure drop across it. The internal automatic devices and mixture control act together to determine the effective size of the metering passage through which the fuel passes. The internal devices, fixed jets, and variable power enrichment valve are not subject to direct external control. Automatic mixture control, AMC. The automatic mixture control unit consists of a bellows assembly, calibrated needle, and seat. Figure 2-27. The purpose of the automatic mixture control is to compensate for changes in air density due to temperature and altitude changes. The automatic mixture control contains a metallic bellows, which is sealed at 28 Hg absolute pressure. This bellows responds to changes in pressure and temperature. In the illustration, the automatic mixture control is located at the carburetor air inlet. As the density of the air changes, the expansion and contraction of the bellows moves the tapered needle in the atmospheric line. At sea level, the bellows is contracted and the needle is not in the atmospheric passage. As the aircraft climbs and the atmospheric pressure decreases, the bellows expands, inserting the tapered needle farther and farther into the atmospheric passage, and restricting the flow of air to chamber of the regulator unit. Figure 2-24. At the same time, air leaks slowly from chamber A to chamber B through the small bleed, often referred to as the backsuction bleed or mixture control bleed. The rate at which air leaks through this bleed is about the same at high altitude as it is at sea level. As the tapered needle restricts the flow of air into chamber A, the pressure on the left side of the air diaphragm decreases. As a result, the pipette valve moves toward its seat, reducing the fuel flow to compensate for the decrease in air density. The automatic mixture control. Automatic mixture control. Boost venturi. Intake air, impact tubes. Main venturi. Throttle valve. Figure 2-27. Automatic mixture control and throttle body. 2-19. Can be removed and cleaned if the lead seal at the point of adjustment is not disturbed. Stromberg PS Carburetor. The PS series carburetor is a low-pressure, single-barrel, injection-type carburetor. The carburetor consists basically of the air section, the fuel section, and the discharge nozzle mounted together to form a complete fuel metering system. This carburetor is similar to the pressure injection carburetor. Therefore, its operating principles are the same. In this type carburetor, metering is accomplished on a mass airflow basis. Figure 2-28. Air flowing through the main venturi creates suction at the throat of the venturi, which is transmitted to the B chamber in the main regulating part of the carburetor, and to the vent side of the fuel discharge nozzle diaphragm. The incoming air pressure is transmitted to a chamber of the regulating part of the carburetor, and to the main discharge bleed in the main fuel discharge jet. The discharge nozzle consists of a spring-loaded diaphragm connected to the discharge nozzle valve, which controls the flow of fuel injected into the main discharge jet. Here, it is mixed with air to accomplish distribution and atomization into the airstream entering the engine. In the PS series carburetor, as in the pressure injection carburetor, the regulator spring has a fixed tension, which tends to hold the pipette valve open during idling speeds, or until the D-chamber pressure equals approximately 4 psi. The discharge nozzle spring has a variable adjustment which, when tailored to maintain 4 psi, results in a balanced pressure condition of 4 psi in chamber C of the discharge nozzle assembly and 4 psi in chamber D. This produces a zero drop across the main jets at zero fuel flow. At a given airflow, if the suction created by the venturi is equivalent to 1/4 pound, the pressure decrease is transmitted to chamber B and to the vent side of the discharge nozzle. Since the area of the air diaphragm between chambers A and B is twice as great as that between chambers B and D, the 1/4 pound decrease in pressure in chamber B moves the diaphragm assembly to the right to open the pipette valve. Discharge nozzle, needle valve, discharge air bleed, accelerating pump suction channel, accelerating pump, main metering jet, C, OPD, vapor vent, relief valve, throttle valve, fuel inlet, pipette valve, fuel pressure connection, fuel strainer, idle cutoff came, venturi, manual idle control rod idle needle valve, venturi drain, venturi suction, manual mixture control needle valve, idle cutoff plunger, vacuum channel reducer, intake air, impact air, chamber A unmetered fuel, inlet fuel pressure venturi suction, chamber B pressure above throttle. Figure 2-28. Schematic of the PS series carburetor. 2-20.